Thanks, Beck. So I'm hi everyone, I'm a PhD student at the University of Warwick. I'm going to be talking a little bit about a project I've been working on using Phantom and MCFOST. That's been going on for about a year or so. So before I get into it, I just want to give a little bit of background and motivation. So I'm sure there are a lot of people in the room who work on hydro simulations of disks and are well aware of the fact that, as Daniel mentioned, disks can have, observations have shown that, there are quite varied morphologies and structures, warps, misalignments, things like that. And these we know that a lot of these properties are probably something to do with interactions between the star and the disk, many of which are affected by properties of the disk itself. But a lot of these properties can sometimes be difficult to directly measure through observations alone. So we can pose the question, is there a slightly more novel way we could potentially constrain some of these? So I've put a few examples here of some papers in the past that have looked at specifically systems where you have a disk or ring-like structure that is occulting a star, and they've used that event and tracked the kind of drop in flux received from the star to infer certain properties of that disk. So for instance, using a light curve like this to figure out things like the diameter of the disk and its optical depth by looking at how much the flux drops from the star as it passes behind it. So my project is looking at a system called HD 98800. So it's a bit of a complicated system. It's got 4 stars. So we've got 2 binary systems. I'm hoping you can see my cursor there. The first binary is the A binary, consisting of stars AA and AB. And then you have a second binary, BA, BB, with 2 stars, and a circumbinary disk, which is aligned about 90 degrees to the orbital plane of the binary. So 2 key pieces of information about the system that make it sort of unique and interesting. We know the stellar orbital trajectories of the stars, the 4 stars in the system, and the alignment of the disk. Those are very well constrained from past observations. And we also know that based on these, this outer binary AaAb is going to kind of, in this sort of direction along this sky plane view of the system, it's going to kind of pass up and travel behind the circumbinary disk around the B binary. So we're expecting the light from these stars to be reduced as they pass behind the disk, and the way in which that happens specifically might allow us to constrain certain properties of the disk. So you might be thinking this sounds very sort of observational. What does this have to do with Phantom at the moment? So this transit hasn't happened yet. It's going to happen over the next few years or so. So in anticipation of that, my work is looking at running Phantom simulations, SPH simulations of the system, and using those to generate synthetic light curves of the transit before it happens. The goal of this is to pose several questions. So what effect do the disk parameters have on what we observe, the actual shape of a light curve produced from such a system? Which set of parameters match most closely what we observe, and how can we kind of make inferences about the disk based on that? And also, how can we use these light curves produced using Phantom and MCFOST to inform observations of the real transit event? How can this kind of benefit observers? So the first step of this method that I'll go through briefly here. So the Phantom disk setup was used to simulate the system. At the time, it had a kind of an upper limit on the number of sync particles that was allowed, which was 3. So this is a quadruple star system. So we needed to allow for a 4th sync particle to be introduced. So the way this was done was by adding essentially this sort of addition to the hierarchical levels of what the code would allow. So previously, the code would allow you to have this binary and then a 3rd single star, and that was the maximum. We just took this code and extended it so that you could convert the single star into another binary and end up with 2 binaries, which orbit a shared center of mass, much like the stars in HD 98800. And then a grid of Phantom models was run using this modified version of Phantom. I'll talk more about that in a second. In order to facilitate the next step, these dump files were then converted to ASCII density grids, which can be done very easily with Phantom. So you had these Phantom outputs, which I think are probably going to look quite familiar to most people in the room. These were then converted to MCFOST density grids by taking this data, interpolating it onto an MCFOST grid that was created. And then MCFOST was run on this density grid to generate an optical depth map so that we could calculate the flux drop from the stars as they pass behind the disk. And so then the third and final step was to take each of these optical depth maps. So we had one created for each time step in the simulation. And for each time step, we could get the XY locations of the stars, A and AB being the stars that are being occulted by the disk. We could use the optical depth map of the corresponding time step to get the value of the optical depth in front of AA and AB. And then the flux drop could be calculated using this very simple formula where F0 was kind of just taken from past observations of the system. So in order to do this, we needed to assume certain disk parameters that had to be put into the simulation. But of course, the goal of this work is to potentially try to constrain those parameters. So I mentioned earlier, a grid of models was created with a bunch of different parameters tested. So that parameter space needed to be defined before we could do that. So MCFOST came in handy for this as well. An initial model was run and SEDs generated for a series of different dust masses, and these were plotted on top of the observational SED data, which you can see with the white dots here on this plot. And I plotted on here the three closest dust masses, three different orders of magnitude that were found to be relatively close, obviously not a perfect match because it is still just a simulation compared to the real data. But these were the three closest dust masses, and then assuming kind of the canonical gas-dust ratio for a protoplanetary disk of about 100, that gave us three gas masses as well by just multiplying these values by 100. So the final grid of models looked a little bit like this. So we have three different gas masses, three different dust masses, and then the final parameter that was also varied was the alpha viscosity of the disk. So the three values for this were chosen based on past studies, theoretical and observational studies that tried to constrain the value of alpha for a disk and found values somewhere on the order of about 10 to the minus 2, 10 to the minus 3. So this column that is highlighted here in yellow is the fiducial model that all others will be sort of compared to see what the differences are. All of these models, one thing to note is these are all run for a simulation time of about 55 years, which was about four and a half decades or so for the disk to have time to wash away any transients, and then an additional sort of 10, 11 years for the actual transit to take place, because that's about how long it takes. But of course, this doesn't allow for any kind of long-term effects to come into play as the two binaries orbit each other over longer timescales. So the second model, the reference model, was actually rerun for a second time for a period of about 1,150 years, which is around about 5 orbits of the wide binary. And by the wide binary, I mean the binary that exists between A and B, the binaries orbiting each other, orbiting a shared center of mass. So this was to account for any possible interactions between the outer binary and the disk and see how that affected the outcome. Okay, so this is the first set of results from the initial run of the reference model, which wasn't run for the longer period of time. This was just run for 55 years. So we can see that the transit begins sometime within the next year or so. And it has these sort of two distinct dips associated with it, which kind of makes sense when you look at an actual video of the simulation. So this is just made using Phantom. The stars obviously pass on top of the disk here, but in reality, they're passing behind it. So yeah, we can see that there is an initial dip corresponding to the stars passing behind this lower half of the disk. As they pass behind the disk cavity, the flux increases again because the stars are not obscured at that point. And then it drops again as it passes behind the upper half of the disk. So that's our reference model. We can now kind of compare all of the other results to that and see what observable differences there are in a light curve. So a model with a higher gas mass, we can see that it, the actual mass in phantom dumps is higher, the scale is higher by a factor of 10, but there isn't really any change to the actual shape or structure of the disk, and there isn't really any observable difference in a light curve either, which kind of makes sense given that the gas doesn't contribute very much to the optical depth. Increasing the alpha viscosity, however, does have an observable effect. So we can see that between the reference model and the higher alpha model, there's a lot more viscous spreading at the outer edge of the disk, especially in the absence of any outer binary interactions with the outer edge of the disk. So that leads to the dips kind of widening, specifically at the outer edges. We see that the transit is kind of prolonged at the end and begins a little bit sooner, but the sort of region where the stars are passing behind the disk cavity, the inner edges, is mostly unaffected. There's not much difference there. A disk with a higher dust mass, however, has an overall higher optical depth everywhere. And so we see that there is a widening of the dips, both at the inner edge and at the outer edge. So the overall transit lasts longer, it begins sooner, it ends later, and the sort of passage of the stars behind the disk cavity appears as though it's shorter. So we almost sort of perceive the cavity as being smaller. And then the final comparison that I mentioned earlier was the one where we allow the reference model to run for longer to account for interactions between the outer binary and the disk. So what we found is that each time this outer binary A would kind of loop around the disk, each time upon each sort of periastron passage around the disk, it would excite these massive spiral arms that you can see here. And as it would pass upwards behind this disk, those spiral arms would get stronger and more prominent. And we can kind of see that in the light curve as well. So you see that the dips themselves are the widest that they've been, not unlike when we had a higher dust mass. But the key difference here is that while all of the previous effects that we've looked at were mostly kind of symmetric, so they affected both of these dips about the same, in this case, there is clearly a much greater widening of the second dip. And that makes sense given that this effect sort of begins when the stars are around about here at the sort of periastron passage of A. And then those spiral arms begin to be excited and sort of grow over time as these stars are passing upwards behind the disk, so that they're at their strongest, just as the stars are kind of exiting the disk. I mentioned earlier that this type of work could also be beneficial to kind of informing real observations of this system as well. So by looking at a light curve like this, we can also calculate the rate of change of flux over time and come up with an estimate for what kind of cadence we would need to take observations at when, specifically when the fastest changes are occurring. So the rate of change of flux is at its highest when the stars are close to the disk inner edge, so when they're just exiting or entering the disk cavity. So if we assume that a sort of minimum roughly 5% change in flux is needed for a change to be detectable, then we'd need to take readings around every 6 days or so at least to be able to pick up on that. And of course, during other periods where the rate of change of flux is lower, measurements can be taken less frequently. So I showed earlier also that the duration of the transit when it starts and ends also depends a lot on certain properties of the disk that we don't really know. The widest possible kind of versions I've looked at, the widest possible transits, mean that we would ideally want to start observing from pretty much now within the next few months for at least sort of 10, 11 years. Actually, the LCO observatory has actually begun observing the system and taking measurements at 2 different wavelengths. So that's hopefully something we can start getting some data on soon. So a quick summary of what I've talked about here. So in short, Phantom and MCFOST was used to produce these simulated light curves of a future transit event where a disk is going to eclipse some stars. And, we found that the disk parameters directly affect what we actually observe. And by comparing those light curves, we can potentially use a light curve of such a system and transit to constrain certain parameters. Am I being given a warning there?
No, I'm just making sure you can see the audience.
Oh, okay. I thought I was my time was up. I am wrapping up either way. But yeah, the main, I guess, take home message for folks at this conference, I guess, would be that this is hopefully a slightly interesting and perhaps novel application of phantom and MCFOST, using it to produce synthetic light curves, which can help also kind of bridge the gap perhaps between theoretical and observational work, and might help in future studies of other similar systems. Yeah, that's it from me. Thank you.
Amena, can you hear me more clearly if I speak into the microphone? Is that better? Cool.
Yeah.
Thank you very much. Does anybody have any questions for Amena? Yes, that's the plan. Yep. My question for you, Amena, are you going to write an observing proposal for this?
That is a plan at some point, yes.
Fantastic. Yes.
Hi, I wanted to know, have you tried to put, assuming that the disk has substructure in the dust, like let's say a planet gap, do you think it would be possible to detect that as the transit occurs? Like, have you tried putting some structure in the disk itself and see if that would be detectable or not?
That's not something I personally have tried, but I imagine it would potentially be detectable, as I guess it would be a region much denser than anywhere else in the disk. But it's not something I've attempted. No, that would be an interesting thing to look into.
Any other questions for Amena? All right. Thank you very much, Amena. Wonderful presentation.
Thank you.